Hello, let's do this question. Find two non-overlapping subarrays, each with target sum. So you're given an array and a target sum. And you want to find two non-overlapping subarrays within the array such that both have sums equal to target and, of course, non-overlapping. If you can't find two non-overlapping arrays equal to the sum, then return -1. So the array could be up to 10 to the power 5. So anything linear is good. Anything n log n is also good. Definitely can't do n squared though. So it has to be, I'm thinking like a linear passes through. We can think of if we do just one pass and just find, let's just think of finding one subarray of length of target. This is a very similar question to the question of finding, I think it was called two sum. No, it wasn't two sum. Minimum subarray of sum equal to target. But this is just an extension to that. But that, to solve the previous one to that, sorry, to solve that one, that was done using two pointer, so which kind of looked like this. IJ, I have two pointers, and because each element in the array is positive, that means we can go increment a fast pointer through the array and try to increment it as long as actually during the first iteration it will be at ij, so j will be at 0, index 0, and we try to increment I as long as it's less than j, and as long as the sum so far between I and j is greater than target. So right now it's equal to target, and it's also not less than j, so we don't do anything. But we see that it's equal to target, and that means we can consider this length here as a possible subarray length. And the length would just be j minus I plus 1. Then we can just increment the fast pointer as we go along. See what the sum is, it's 5. And then try to increase I as much as possible so that it fits those two conditions where it's less than j and the sum is greater than the target. Well, it fits both, so we can increment it up to here. And that's the end of the second iteration. We check that the sum is now 2, but that's not the target, so we can skip whatever condition there is there. Then we get to 4, sum of 4. Try to increment I as long as it's greater. Yep. Then j increments. We get 6. Try to increment I as much as possible. Still greater than, but I is not. I has to be less than j to increment it. Okay, so we keep incrementing j. That's too much. Then we increment this, and then we found this 3 and 3. So that's the answer. And we just have to return the length of the sum of the lengths of the two subarrays. So in this case, it will be 1 and 1, so 2. Okay, but there is a problem with this approach of just trying to find two. Like, what if say, for example, we have 1, 1, 1, 2, and then we have a 1 here. Okay, in this case, let's see what happens. Well, I'll increment j to get 3. Record that as an answer, so length of 3, and then I can, once I find that, try increment I as long as the sum is greater than, okay, but it is already equal to, so that stays the way it is. So I increment, and then now it's like 2 1 1 1. So that's 5. It's too much. So I increment this as much as possible to get down to 3. Okay. Well, I found this one. That's a subarray of length 2. Before it was subarray length 3, but now we see they're overlapping. That's not good. Well, maybe we could maybe we could keep track of the last subarray, subarray's j value. So this one here, and then check if it's if the left end, if I of our new subarray is less than or equal to the previous's right end. If it is, then they're overlapping, and so I'll just replace the last one's length with my new length if it's shorter. Okay, so that could work. But then let's look. So then I can increment j. It's too much. I increment this. Oh, that's another answer. But then that replaces my previous answer because they're overlapping. And then I'll only get one subarray in the end. So that's not good. But there is actually an answer for this, and that's this subarray here and this subarray here. So I'll be missing that case. So definitely one pass through using the normal approach doesn't work. So how can we deal with this? Well, what if we use DP, where DP could be, we have a suffix DP, no, prefix DP. Of I is equal to the minimum length of a subarray equal to the target at any position. So length of subarray with sum equal target. Length of subarray with sum equal target. And within range 0 to I. Alright, so then for any value here, I know the best answer that I can find within the subarray from here, within here, within here, within here, right? So I would just actually do the same approach, but just keep track of this information in an array and store an array. But that's not enough, of course. We're only keeping track of the min length of one subarray. We also need to keep track of another subarray. Let's call it, so this is prefix suffix. So it will be the min length of a subarray with sum equal to type with range from I to the array.size. So if there's n items in the array, then n minus 1. Yep. Now, how would you actually figure out using these two arrays the answer? Well, the answer has to be, because the arrays aren't overlapping, the answer has to be has to be on either side of a partition of the array. So we can choose one partition of this array. So like say this comma here, or this comma here. Then if we find the best answer for this subarray and this subarray that we can get from just these dp's, then there will be the answer for a petition at this comma. Then we could just go through each of the petitions, so each of these commas, and check at each point what's the best answer for the two subarrays that it creates, this side and this side, using these answers. So going through each petition, that will definitely give you definitely go and give you the right answer. If we take the minimum answer out of all of those. Right, so that I think that makes sense. Okay, let's try actually calculate the time complexity. Well, to calculate prefix dp, it's just a linear pass-through using two-pointer approach. That's because I and j, when we did that thing we did initially, that I and j only ever increment, they never decrement, which means at most we're going through the array twice to calculate one of these. So that's going to be linear. And then to go through each petition, that's also linear. And to find the minimum as we go along, that's also linear. No, that's constant time as we go through. Yeah. So time complexity is just fine. Space complexity is also O of n. But that's fine. Who cares about space? Okay, I'm just kidding. People do care about space. How do we implement this? Well, we need a vector. So we need the prefix dp and the suffix dp. And let's initialize everything to infinity, because we need a way to represent that a subarray is not possible. A subarray of sum equal to target cannot be found within a certain number here. So we can say array.size int max as that. Cool. And also a suffix. Let's call it p dp and s dp. Cool. Now let's calculate the we actually just have to do both individually. So prefix would go through from left to right, suffix we have to go from right to left. From left to right, we would have a for loop. I like to have it so that I is less than j, and same for when we're doing the suffix. So the fast pointer here would be j, and we'll start from 0. J less than array.size plus j. And as j goes through, we also need to keep track of an I and a sum. So current sum is equal to 0. And then add to the sum whatever is in the array at j, at the fast pointer. And also, I need to, like I said before, keep incrementing I until while the sum so far is greater than the target and I is less than j. So while I is less than j and the current is greater than the target, then keep incrementing I. But if you increment I, you also want to decrement the sum. So minus equals to the array at I. But you also want to decrement I, so we could do a post decrement. That's a nice, neat way to do it. Then we can check whether... then we can set the current... we can set the current dp, so pdp is equal to... pdp at j. Let's make that equal to pdp, the previous dp, dp at j minus 1. but we want to check if that's less than 0. Let's make it int max. Let's make it we need to have j minus 1 here. So if j minus 1 is less than 0, let's make it int max. Otherwise, just do j minus 1. Now so now that I have just like making the current equal to the previous, actually I want to consider the current target the current sum if it's equal to target. So if the current is equal to target, then I want PDP j to be equal to the min of itself and j minus I plus 1. So the current length of the array. Yep. And that should do it. So let's do the same thing, but for the suffix. We would have to set the current to be equal to 0 again. This time define a j equal to 0 and have this as I. So I is the fast pointer that needs to decrement while it is greater than or equal to 0. And it starts at array.size minus 1, the last one. Current plus equals to current I, and then while j is greater than I, and the current is greater than target, decrement j sorry, wait. This is not decrement, this is increment, my bad. This is decrement. Yep, okay, that seems to work. PDB j minus 1, yes. Okay, so let's set spdp, so that's the suffix, to be if I plus 1 is greater than or equal to array.size. We could just say equal to, but it doesn't matter. Greater than equal to array.size and make it int max, otherwise do SDP at I plus 1. Then if it's equal to target, I want to consider changing SDP to be the min of STB, whatever is already inside, at I, and then j minus I plus 1, just still the length of the array. Cool. That seems to work. And then, once we have both the suffix and DP, we go through each petition. So the petitions we can think of like int I is equal to int I is equal to 0, I less than I less than array.size minus 1. We're not going to go to the last element because the petitions would be we're basically going through every pair of elements, and those pair represent the petition, the right end and the left end of the two petitions. So that's why we don't need to go all the way to the end. We need to keep track of an answer, so the best answer so far. Let's make it int max initially. and then do we need to check that the best answer so far is not int max. So if the PDP of I does not equal to int max, and SDP of I plus 1, yeah, does not equal to int max, then there's a possible answer here. So let's do the answer is equal to the min of whatever is already in the answer, and PDP of I plus SDP at I plus 1. Yes, that checks out, that does check out. And then we return if answer is equal to int max, return -1, otherwise return answer. Alright. Let's debug it because I don't expect it to work. Let's go. Okay, we get -2. Interesting. J should start at the end. Of course. Array.size -1. I think I made the same mistake last time. There we go. Yay.